Welcome to a video on the Colpitts oscillator. In this video we will have a look at properties and applications of a Colpitts. Then we will do the derivation using Barkhuizen's criteria. Then we will look at some variations and improvements that you can make to these oscillators. We will do a design and then some simulations to verify our design. Okay, properties. The Colpitts oscillator uses a LC resonant tank to set the frequency. The oscillator is self-starting, and although you can drive the output to a very high voltage, almost to saturation, an LC tank has a very high Q factor, so it basically filters the output. So we do not require additional nonlinear amplitude control with these. And if you do it with a BJT, it also uses the non-linear region of a BJT to self-limit the output. Okay, with LC tanks, we can also generate very high frequencies, and we can implement these using BJTs or MOS. We can also implement it using op-amps, but it has frequency limitations with op-amps, typically 100 kilohertz, depending on the gain bandwidth. Okay, something to keep in mind that the BJTs and MOSFETs has parasitic capacitances that influences the oscillation frequency. So you can design for one, but due to the parasitics, your frequency can shift a bit. This is one of the effects that we ignore during the design process. Okay, and most of these LC tunable oscillators can be tuned by adding a single variable capacitor. So you will find these typically in FM transmitters, intermediate frequency mixers, in RF applications, measuring equipment for clock generation. To be honest, the list of applications is extremely long. This is just in broad terms where you will find them. Okay, if we look at the two figures, one is BJT implementation, the other is the op-amp implementation, and both of them has the LC tank. Okay, so for the Colpitts, it's two capacitors and one inductor in this kind of pi configuration that you'll find here. And this is our frequency selective network, also called the resonant tank circuit. Okay, so for the BJT, we require some bias and there is some DC involved. So we need to include a DC blocking capacitor here at the input. And for amplifier like this, the gain is minus the transconductance multiplied by the collector resistor, and this at room temperature is approximately minus 40 IC RC. So we can choose a collector current, choose a collector resistor here to set the gain. Okay, this is also inverting amplifier, so the LC tank also needs to bring its own inverting effect so that we can have positive feedback in the system. The op-amp implementation is quite simple. We have our negative feedback here, which gives us our gain, and our LC tank is in the feedback path. Okay. So, what it boils down to is we have an amplifier, and the gain is minus AVV in with output impedance flowing into our tank circuit. So, from the amplifier's perspective, we see a voltage divider of R out and all these impedances in parallel. And for the feedback network, we also see a voltage divider between Z3 and Z2. Okay, so this is if we neglect this impedance sitting right here. Okay, so the first voltage divider is the inductor and the second capacitor. So Z2 over Z2 plus Z3. And that is also our frequency selective network. So if we just add these impedances in there, we have our beta network. Then we can define our parallel seen by the amplifier. And this is the series combination of Z2 and Z3 in parallel with Z1. And our amplification thus is minus AV ZP over R out plus ZP. Okay, so that is our loaded amplification. Right. Then I suggest you leave it without the capacitors and the inductors for the beginning. And this is the voltage divider, and we multiply with our frequency selective. And as you can see, these two terms cancel immediately, and we are left with our amplifier looking like this. Multiplying with this summation of Z1, Z2, and Z3, we are left with this bottom equation. Okay, now you can insert all your capacitors and inductors. And it will reduce to what we see here. So all our concerns of imaginary terms is here with our unknown output impedance of our amplifier. So the goal is to have all our imaginary terms to be 0, right? So that will be our oscillation frequency. So L omega 0 minus 1 over capacitor 1, 1 over capacitor 2, and we are left with 1 over L C1 C2 over C1 plus C2, and we take the square root of that. Okay, so that is our resonant frequency. So this whole term will disappear, and we need to basically add our omega squares in when we're trying to find what our gain should be. Okay, so what's left is this whole term here should be equal to 1. Okay, so we can get everything standing alone, and we add our omega 0 squared in, and it will reduce to that our gain should be capacitor 2 over capacitor 1 to start the oscillation. So basically, our gain should be higher than the capacitor ratio. So for op amp, R2 over R1 should be larger than our ratio. For BJT without the gain stabilized, GMRC should be larger. And if we add an extra emitter resistor for stabilization of the gain, that middle equation should be satisfied. Okay. So, some improvements that we can make is taking away the collector resistor and adding a RF choke. Okay. This will make that we have rail-to-rail output, and the much closer we come to the resonant frequency of RF choke being in resonant with a tank, your output can even increase beyond your rail voltages while being a sinusoidal wave. Okay. Emitter resistor 2 can be added to decrease the gain, and by doing that you increase the bandwidth of your op amp, of your amplifier. Okay, lower gain, wider bandwidth. And you can use RE1 to ensure that your collector current is stable. Right, so in a simulation I ran the LC tank and got the boat plot, and you'll see that there's a resonant peak right here. So nothing out, then boom, you have a resonant peak. Okay, so your LC tank, you should ensure that the bandwidth of your amplifier is over the resonant frequency of your tank. Okay, so if these don't match up, if this tank frequency is outside the bandwidth, your oscillation will be extremely small and your oscillator will be worthless. Okay, if you add a RF choke, remove the collector resistor and add a RFC, the closer that this resonant peak of a choke comes to this LC tank resonant frequency, the more your output will increase. Okay, so ideally these two should line up. Something but fun with to play in a simulation. Okay, so for the design, I wanted to pause the video and go and design these two circuits. I wanted to design a Colpitts oscillator with oscillation frequency of 10 kHz. So I just went here with a low frequency so that we can use a BJT as well. Use 12 microfarad capacitors for the LC tank. So basically choose C1 and C2 as 12 microfarads. And calculate and select the standard inductor to get 10 kHz of oscillation. Then I wanted to do op amp design and choose again slightly higher than the capacitor ratio and use plus minus 10 volt sources. Okay, simple enough. Then design a BJT amplifier with a 1 milliamp bias current and stabilize the bias and design for maximum swing. Use a positive 10 volt source. Simulate the problem and then add a RF choke to see the difference in the outputs. So pause the video here and we will be back in a moment for the solutions. Okay, the solution using an op amp. Picking the two capacitors with same value and adding them in here will yield an inductor value of approximately 47 microhenries. Our capacitor ratio is 1. So if we choose our amplifier's input resistor as 1 kilo ohm and R2 as 1.2 kilo ohm, our gain is definitely higher than our capacitor ratio and our oscillator will start up. Okay, we will verify this in simulation after the BJT design. Okay, so this is kind of simple to design. Right, so for the Colpitts using a common emitter amplifier, these values will remain. Okay, let's see how our 40 ICRC compares to 1. Basically, a collector resistor for our 1 milliampere design should be higher than 25 ohms. Right, designing for maximum swing and stabilizing the collector current, our collector resistor and emitter resistor should be the same values, and we divide our VCC over the two resistors and the transistor, so VCC over 3 divided by IC yields a collector resistor of 3.3 kilo ohms. Okay, so our oscillation will start with this collector resistor choice. Okay, then all the other capacitors in the circuit is low frequency capacitors. So choose fairly large values here so that you increase the low cutoff frequency of the amplifier. Okay, the biasing resistors. 3.3 kilo ohms will yield in a 3.3 volt drop at the emitter, plus our VBE should be 4 volts. Okay, taking our VCC, dividing it by IC over 10, this is the rule of thumb, yields 100 kilo ohm resistance in total for the two base resistors. Calculating RB2, this is the resistor at the base of the transistor, gives us 40 kilo ohms, so 39 kilo ohm E12 value. And RB1 will end up to be a 68 kilo ohm resistor. Okay, so there is our design done. So I'm gonna jump into the simulator and let's verify our results. So here is our Colpitts implemented in simulation. I use a non-ideal op-amp for these simulations to ensure that we have startup and don't have to do any magic tricks with uh, the input voltages, and the startup will work straightforward. So yeah, let's run this and see if it works. Right, so there is our output. Let's zoom in a bit. And we have nice sine waves going from the limits of op amp. Okay, the TL074 has roughly a 2 volt saturation limit, so 10 minus 2 is around about 8. Okay, so this follows our amplifiers rail limitations. Okay, so this is definitely working. Let's view FFT of this data, and you'll see there is much less harmonics than any of our other oscillators that we have. And our 10 kilohertz is a bit off here, but this looks really, really nice. Okay, let's jump over to our BJT implementation. Here I have our BJTs, so the one with the RC still and one with a very large RF choke. Let's run this. There's our simulation done. Let's check our frequency here at the load. And we have a plus minus 4 volt swing, plus minus 2 volts, sorry. And we have about 6 volts available over here, but this is self-limiting itself, and some of these capacitors could be bringing down my amplitude, but this sinusoid kind of looks nice. Okay, if we go over to the choke version, we have 4.5 to minus 4.5 volt swing, and this is also very nice sinusoidal wave. So you tend to use your amplifier to its full potential, and the larger you make this choke, the better this result will become. So let's quickly compare the two in FFT. And there we go. Almost similar, just higher amplitudes, minimum noise. If you want the FFT to be a bit more accurate, we need to increase the amount of data that we see. So let's start recording from 100 milliseconds, run. Close this. Alright, with more data available, let's try the FFT again. And this should look much nicer. And there we go. Bit more noise, but there is our two FFTs. And that is it for the Colpitts oscillator. Thank you for watching.